Uh, in this video, we'll discuss two more ways to evaluate, right? Two more methods to evaluate a limit of a function at a given point. So the first we want to discuss is coming from a very a fact we have discussed. And when we introduce the limit of a function, we discussed the limit on the left side and the limit from the right side, right? So we have a conclusion there, which is what? Which is as x goes to a here, f of x equal to L, right? So function value is getting closer and closer to L from both sides. If and only if and only if. And on the right side, as x goes to a plus, recall that a plus means greater than a, but getting closer and closer to a, right? So that's the meaning of a plus. If you want to sketch it using a graph, you have fixed point A here. So a plus is on the right side, right? Getting closer and closer to a on the right side. And a minus is getting closer and closer to a on the left side, right? So on the right side, for sure equal to L, and also and left side also equal to L, right? F of x also equal to L, right? So let's say example, how do we apply them? For what kind of limit, what kind of functions we can apply this fact, right? So normally, if you have a function, left side, right side formula will be different. And for sure, we want to discuss the right limit, left limit. If they agree, the limit equal to whatever you get. If they do not agree, the limit of that at that number doesn't exist, right? So let's see a quick example here. We want to evaluate the limit of this. Example. Now, what is the limit as x goes to 0, right? X over the absolute value of x. Right? We want to know what's this limit, right? And clearly, you cannot cancel the 0 factor because x is not the absolute value of x, right? Because sometimes x is negative. By the definition, we know that the absolute value of x is either x when x is greater or equal to 0, or negative x when x is less than 0, right? So that's what we know about the definition of absolute value, right? Okay, so we cannot cancel 0 factor. We want to find a good way to cancel that. Now you can see that divide this limit to limit from right side, limit from left side. You can apply the definition here to simplify your function form, right? So let's try to do the limit from right side. So x goes to 0 from right side, x over the absolute value of x, right? So x goes to 0 from right side means what? X is greater than 0, goes to 0, and x is positive, right? So there's two conditions. So by our definition of the absolute value, so this equal to as x go to 0 on the right side, x over x, because when x is positive, the absolute value of x is just x. So this is same as x goes to 0 on the right side by some algebra. We know that x over x is 1, so this is 1 here. So this is 1. So we know that the right limit is 1, right? So let's try to look at the left limit. As x goes to 0 on the left side, x over the absolute value of x, right? We know that x goes to 0 from left side means x is getting closer and closer to 0, getting closer and closer to 0, and x is less than 0, right? So this is equal to, as x goes to 0 from left side, x over negative x, because the definition of absolute value when x is negative, the absolute value of x is negative x, right? So this is equal to, as x goes to 0 from left side, x over negative x by some algebra, this is negative 1. So this is negative 1, right? So, right, we know that 1 is not negative 1. So hence, our conclusion here is using our fact, right, x goes to 0, x over the absolute value of x does not exist, right? Does not exist, right? Sometimes we use DNE to represent does not exist. Okay, so let's see the other way to evaluate a limit, right? Which is our squid theorem. I will see a couple examples to which we can apply our squid theorem, right? All the different techniques apply to different functions, right? And so this happens. So let me try to sketch a picture here, right? So we have our XY plane here. We have three functions, which is, this is blue one is our function y equal to h of x, and this red one here is our bottom function, which is our y equal to f of x. Now we have a function in between, right? Let's use black or orange. The function might change crazily, but always lie in between f and h. This is our function g, which is y equal to g of x. So this is our point A here, right? You can see that if your top function h go to a place as x goes to a, your bottom function f also go to the same place. Whatever in between will be forced, will be squeezed into the same point at that number, right? So that's basically our squid theorem. So we say that if f of x is less or equal to g of x less or equal to h of x, when x here is near A, right? When x is close to A, this happens, right? When x is far from A, we don't care. We want to know what happens when x is getting closer and closer to A. So when x is very far from, we really don't care. And and also we are given one more condition, and both the upper function, which is our h of x, equal to the limit, both limit, and lower function, which is bottom function, which is our f of x, equal to A. Then what happens here is, then our conclusion is, then the middle function in between, so will be squeezed into the same place. X goes to A, g of x also equal to A, right? So this is what happens. Normally, you are given a function g. This function has a natural upper bound. You have to identify your upper bound and lower bound. Then make sure both lower bound and upper bound go to the same place. Then you know the limit of the function you are given, right? Let's see a quick example. We are given a function which is x squared times sine of 1 over x, right? So this is clearly a very complicated function, contains square, contains sine, contains 1 over x, right? We want to know what's the limit of this function as x goes to 0. Again, here you cannot plug in 0, right? If you plug in 0, you get 1 over 0, which does not exist, right? And also, you cannot cancel x in the denominator because whatever inside the sine function cannot be canceled outside, right? Which is that's against our algebra rule, right? So, right, all our methods discussed before doesn't work, right? How do we do that? We want to use our square theorem, right? So we want to get a lower bound and upper bound of our function, and both our lower bound, upper bound. You don't want to make your upper bound very big, which means it's impossible to control, right? So what's the natural upper bound? We know that by the trig functions, sine of theta has a very natural upper bound, which is 1, and a very natural lower bound, which is -1, right? So which means we get a very good upper bound and lower bound for our second factor from -1 to 1, right? And we also know that x squared is positive, right? Which means when you multiply by x squared on both sides or 3 sides, right, left, middle, right, of our inequality, the direction of the inequality doesn't change, right? You get negative x squared less or equal to x squared times sine 1x less or equal to x squared, right? So this is a good control of our function. Why is that? Because first, we know how to evaluate the limit of upper and lower bound. That's easy quadratic function, right? And the second, their limit are both 0 as x goes 0, right? You can see that as x goes to 0, x squared equal to 0. Also, as x goes to 0, negative x squared also equal to 0. So both upper and lower bound converge to 0 as x goes to 0, right? So we can apply our square theorem now. So by the squeeze theorem, we get that as x goes to 0, x squared times sine of 1x equal to 0, right? This is a typical application of square theorem. And so, yes. And